All right, continuing on with forces. So by the end of today, I will be able to calculate the acceleration of an object when All right, carrying on with forces. By the end of today, I will be able to calculate the acceleration of an object when given the resultant net force acting on the object and its mass. I will also learn this as Newton's second law. Quick recap though, and these are really important pieces to know from the previous lesson. When an object has a net force of 0, that means all the forces combined, when you add them all together, if it results in a 0, the object can either be at rest or moving at a constant velocity. You have to know this. So today we're going to look at what happens if the net force on an object is not 0. So that's today's lesson. Okay, so Newton's second law of motion. Okay, so if I load a cart with progressively more weights and apply a constant force each time, what happens to the acceleration of the cart? Okay, so I've got a little video that's going to follow, but if you want to think about that for a minute and make a guess. Okay, so we have a little demonstration here. I have two carts that are the same mass. I have 500 grams on both of them. This is just my blocker to keep them from rolling away. I'm going to put two different masses on the end here. This is 20 grams. This is 200 grams. I'm going to just wait before I put that on there. So the investigation is the carts have the same mass. This string here will represent a constant net force that's applied to both carts. Okay, so we're holding mass constant and we're changing the F net. So what we should see is how does that affect the acceleration of the carts. So the heavier or the larger force is going to be in the front. Keep that in mind. So I'm going to put this on here. You can probably make a pretty good guess of what's going to happen. So let's just recap. This has the larger F net. This has the smaller F net. The masses of the carts are the same. Okay, so not a big surprise there. The cart that had the larger force had the larger acceleration, which is kind of what we expect. Okay, this is the second round of this test, so now I've changed the situation. Now they both have the same F net. Both of these masses on the ends here are the same, so they're going to have the same force applied to each cart. One cart has 500 grams, the other cart has 1.5 kilograms or 1500 grams. So the cart in the back is 3 times more massive than the cart in the front. Okay, so what I'm going to do is when I pull this lever away, we're going to see which cart accelerates with a greater acceleration. Will it be the cart that's heavier, or will it be the cart that's lighter that has the greater acceleration? So I'm just going to take this mass out of here, and oh, it's ready to go. Okay, so without crashing through my living room here, what we found was the cart that was less massive accelerated quicker. Okay, so we held the force constant, we had a smaller mass, and it had a greater acceleration. That's known as an inverse relationship. So the more massive cart back here had a smaller acceleration. And when we see the formula in the next slide, you'll see how that comes together. Okay, so as we saw in the video, there's some sort of connection between the force acting on the object and the mass of the object. Okay, we can play with a whole bunch of different types of carts like that and come up with these relationships. But here's the second law of motion and its sort of formal definition, and it's a bit wordy. If the net external force on an object is not 0, so that means there's some unbalanced force, the object will accelerate in the direction of this net force. So that's the little string that was attached to the carts. The magnitude of the acceleration is directly proportional to the magnitude of the net force. So if you have a bigger force, you should accelerate at a quicker rate. Okay, and inversely proportional to the mass of the object. So if you have a really big massive object, it's going to take more force, or it'll have a smaller acceleration. Okay, so that's all pretty wordy. So let's just try and break it down a little bit easier over here. If the mass of the object remains constant, it takes a larger force to create a larger acceleration. Okay, that makes sense. If the force applied to the object is constant, a smaller mass will accelerate faster than a larger mass. Okay, and so we have this relationship here, F net equals ma. Okay, so if you hold one of the variables constant, then you can see how the others behave. Okay, so if we held, for example, say we held mass constant, if the F net went up, then the acceleration would have to go up to match it. Okay, if we held the accelerator, let's say the mass, let's say the F net we held constant. So if we held this one constant, if the mass went up, then the acceleration would have to go down to balance it. Okay, so that's a three-variable equation. We can play with those things. The calculations, at least, are fairly straightforward, as you'll see in this example. Determining acceleration. Okay, so a net force of 36 newtons forward is applied to a volleyball of mass 0.24 kilograms. Determine the acceleration of the volleyball. So the first thing I'm checking is, do I have the right units? And I have newtons and I have kilograms, so that makes me happy. Okay, so I've asked for find A. So I have my equation, F net equals mass times acceleration. Okay, so I have the force, I have the mass. Finding A should be fairly straightforward. Okay, so there's my equation. I can rearrange the equation, or I can put the numbers in now, whatever I like, and then I just do the division, and I come up with an acceleration of 150 meters per second squared forward, which is a really big number, but you have to remember the force that's applied to the volleyball is only for a very small fraction of time, so it's not going to be coming out of there like a rocket ship. That'd be a very dangerous volleyball game. Second question, calculating net force. So a 64 kilogram runner starts walking at 3 meters per second to the east and begins to speed up for 6 seconds, reaching a final velocity of 12 meters per second. Calculate the net force acting on the runner. So there's a bit of information that's hidden here. So here's my F net, and F net requires mass and acceleration. Well, we have mass, check, but we don't have acceleration. So this is where we have to be a little bit more cautious, is that this right here goes back to our first unit with kinematics. So we may have to pull out some of our kinematic equations to use that information to come up with our acceleration over here. So as you can see, we've laid out, there's our F equals ma, and there's our kinematic equation. Okay, so if we substitute the values into the kinematic equation, I come up with acceleration, and then we can substitute it into the equation, and we come up with a net force of 96 newtons to the east. Okay, so next question. We have a 9,100 kilogram jet moving slowly on the ground and fires its engines, resulting in a force of 22,000 newtons to the east and a force of friction on the jet of 3,800 newtons to the west. So draw a free body diagram for the jet. So we already have that, just to save a little bit of time. Okay, what we do want to highlight though within this question is it says nothing about the airplane or the jet going into the air. So there's a bit of an interpretation that it's just moving left to right. There's no up and down directions, or sorry, no up and down movement in this problem. So we're going to assume that those forces have to be balanced. Okay, so if we look at our F net vertical, if we looked at our F net, we would have to have our normal force minus our gravitational force, but because it's not moving in the vertical direction, our F net has to be 0. And we can see from here that in this case, because the jet is not moving in the vertical direction, the normal force will have to balance the gravitational force. Okay, so now if we look at the horizontal forces, I'll change color to green. If we write an F net statement, we would have 22,000 minus 3,800. Come on, there we are. So our F net is 18,200 newtons. Okay, so now the net force, though, we can rewrite. F net can be replaced with mass times acceleration. So if I have all of that equal to 18,200, the mass of the plane is 9,100, and you can see I'm going to get some really nice numbers here. So when I divide that out, I get an acceleration of 2 meters per second squared. Okay, so we've got the acceleration of the jet, we've got the net force acting on the jet. It's only the vertical, only the horizontal direction. This is our F net here. Okay, it's the unbalanced force, and there's no change in the vertical direction. Okay, so Newton's second law, and if we connect that to gravity, so previously we found that for Fg we had mass times the acceleration due to gravity, where m was the mass of the object, and g represents the acceleration due to gravity, and it's 9.8. So if we compare the formulas we just developed with Newton's second law, F net equals ma and Fg equals mg, you'll notice they're the same. The only difference is because g is a constant value, they gets a new symbol, but it's still an acceleration, so both problems end up being force equals mass times acceleration. Okay, and this is a concept analyzing problems as parts versus systems. We're going to do more of this in the next 2 lessons, but just to get your mind thinking about it, if you have 2 blocks that are attached with a perfect chain, so no mass, no stretch, we could investigate some parts of the system or the entire system. So if we were to look at this in terms of its parts, we could investigate just the forces acting on the 10 kilogram. We could investigate just the forces acting on the 20 kilogram, or we could start to look at this thing as a whole system, and that would be as if those 2 things were combined. Okay, so either way, that applied force of 100 newtons, it doesn't know whether there's a 20 and a 10 linked by a chain or a 20 and a 10 stacked on top of each other. Okay, so that's just something to consider as we move into more challenging problems in the next day or 2. Okay, so if you could pause and try these, please. So your answers are in your textbook, so if you don't want to listen to me go through them, all those hidden answers are in your textbook. Just go to section 3.3 and look it up. So pause it now and try a couple. Okay, so hopefully you've had a chance. I'm not going to do all of them, but I'm going to highlight a couple of the thoughts behind some of them. So a net force of 126 newtons, 70 kilogram sprinter. We're looking for acceleration. This is an F equals ma problem, and the answer should be 1.8 meters per second squared. Okay, so I'll just give you the highlights on how to solve some of these. A car accelerates at 1.2 meters per second squared, so we have an acceleration here. Okay, the net force, so I have an F net. Okay, what is the mass of the car? So we are back again to this expression. So by the time you calculate that, we should come up with about 1,300 kilograms. A cyclist starts to pedal vigorously, increasing her velocity from 6 meters per second to 14 meters per second. Okay, in 6 seconds. So you can probably already see where this question's going. Okay, we're going to have to do some sort of kinematic expression to come up with the acceleration. So using here, 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 we can come up with the acceleration. Okay, we have the mass of the bicycle, and we're trying to find the net force. So again, we're back to our F equals ma, but to get the a, we have to use our kinematics. Okay, so by the time you do that, you end up with 77 newtons to the east. During a road test, the driver brakes a 1,420 kilogram car, so I already have my mass for this next problem. Okay, we're moving at 4.8 kilometers an hour, so right there, that dude should make you a bit nervous because it's in the wrong units. Okay, we'd prefer to have these in meters per second. The car slows down and comes to a stop. So a stop means our VF is 0. Okay, and after moving 729 meters to the west. Okay, so if you look at this, this is a VI, this is a VF, hidden under here with the word stop, and we have a D. So if you think of your kinematic equations, oh, I can't remember, it's 2AD, 2AD, yep, I gotta get that out of there. To AD. Okay, so if you look, we have our final, we have our initial. We're trying to find the acceleration because we want to find the net force. Okay, so we would use our kinematics to figure out what A is. A goes into your F net equation, and we can come up with the net force acting on the car, and we should find it is 316 newtons to the east. Now the next question is, what is the force of friction acting on the car while it's slowing down? Well, there's only one force that's acting to slow it down. Okay, and that is the force of friction, so we should find those two answers are the same. For each, number 5, for each free body diagram below, determine the net force applied to the object and its acceleration. Okay, so we'd first have to find the net force, so our F net here. Okay, we can sum that up. It's going to be 31, 55, 45, 36 newtons. Let's say it's to the west. Okay, so let's have a quick look at the solutions. Okay, 36 newtons to the left. We know the mass of that box, so again we can use our F equals ma equation and figure out what the acceleration is. In this case it's 4.5 meters per second squared to the west or to the left. You can do the same thing in this problem. You will notice though, conveniently, okay, a lot of the forces will cancel off, so these two here cancel off, so we're really just doing a vertical problem. In grade 11 you should expect that. We should really just be doing one directional or one dimensional force problems at this point in time, so look for those forces to cancel. Okay, and again the same thing, we get our F net, we know the mass of the object, we can use that to come up with our acceleration. Okay, the last question, and I know I'm going a little quickly here, but we do have time constraints. In a two-person bobsled competition, athlete 1 pushes forward on the sled with 310 newtons. So I'm going to model my sled with a box. We're going to say 310 newtons in that direction. Athlete 2 pushes forward with 354. Those are both newtons. There's a force of friction of 40 newtons. The mass of the bobsled is 390 kilograms. Calculate the acceleration of the bobsled. So we would start with an F net statement. We would have 310 plus 354 minus 40. So 310 plus 354 plus, minus 40 is 624. I can replace F net with mass times acceleration. Okay, the mass of the sled is 390. And if we divide both sides by 390, we should get 1.6 meters per second squared to the right, or whichever direction you called it, forward. Okay, and there's your answers. A little more practice if you want. You can find a few more questions at the end of the textbook. Section 3.3, 1 to 5, number 8 are all good choices. Thanks for tuning in.